All right, section 4.6, coloring graphs. So coloring, chromatic number, and dual graphs we'll be covering in this section. So it often happens that we use edges to describe a relationship between the objects that we use as vertices. So the objects are the vertices, and then the relationship are the edges. In this instance, we will use the teams in the office, a problem that was discussed on page 204, as the vertices, and we'll use the edges between the vertices to indicate that the teams share a member, that there's something going on in between. And so it's kind of like in this particular situation, kind of flipping that around a little bit. So kind of just like giving you a little heads up on that thought process. You're like, wait a second, in the past we had these relationships. So jumping in, a number of different problems can be solved by building a graph that models the problem and then labeling the vertices of the graph in such a way that no two adjacent vertices have the same label. So the key right there is no two adjacent vertices have the same label. Without loss of generality, we can think of the labels as being colors. And so that's where the coloring part comes in. For example, the office manager, page 204, we named the possible time periods with colors. Hence, in this section, we'll examine this problem. So go ahead and take a minute if you haven't and take a look at page 204 at the problem with the office manager and trying to find the groupings. We're going to jump right into it. So given a simple graph, what is the smallest number of colors that can be used to assign a single color to each vertex so that no two vertices have the same color? So that leads us to two definitions. These are our key definitions. And the first one is coloring. A coloring of a simple graph and an assignment of color to each vertex in such a way that no two adjacent vertices have the same color. So there's the key thing. No two adjacent vertices. So that's really what this comes down to. So no two adjacent vertices. So in kind of making sure we understand what that means. So the chromatic number is simply the least number of colors necessary for the coloring of the graph. So pretty straightforward. So let's take a look at a couple examples. So take a look at graph G, and we want to find a color. We want to find a chromatic number. So to do that, we have to color it first. So to color this, to start off, we use three colors. So vertex 1 was red, then we did blue, and then we did red, and over here we went green, and then we went blue. But then we realized that, wait a second, it's not necessary for vertices 3 and 4. So vertices 3, let me grab my colors here. So vertices 3 and vertices 4 to have different colors because they're not adjacent. And so they're not adjacent, they can have the same color. So if we started with red and then went to blue, we could go back to red on both of those and then go back to blue. So we see that in figure 3b, where we do our coloring, where we go red, blue, so non-adjacent. So V3 and V4 are not adjacent. They're adjacent to blue, so they have to be different than blue, but red can be used again. And then we can go back to blue because once again, V3 and V4 are not adjacent. V5 is not adjacent to V2. So therefore V5 can be blue. So in this particular case, this is not an accurate coloring. This is our accurate coloring. And therefore our chromatic number is 2 for a graph because of the fact that we only needed 2 colors. Let's take a look at graph H. So in graph H, one thing that we want to pay attention to when we jump into this problem is this idea that not only do we have, let's call this vertex 1, vertex 2, vertex 3, and vertex 4, not only are they adjacent to each other, like vertex 1 and vertex 4 and vertex 1 and vertex 2, but vertex 1 is also adjacent with vertex 3 because of this line crossing the middle. So because of that adjacency, then we have to make sure that we have colors that represent the 4 different possible, that's not the right way of saying that. We have to make sure that we have colors to, I don't even know. I'm just going to back up and take a deep breath. All right, so here we go. So since we have 4 different vertices and each vertex is adjacent to each other, we will need 4 different colors. And so we can see in this representation, this would be our accurate coloring. And so since we have an accurate coloring, we would know that our chromatic number for this guy is going to be 4. I'm going to hit pause for 1 second and we'll pick back up with the rest. All right, so picking back up, so now we're going to take a look at the application of graph coloring. We're going to introduce this idea of dual graphs. So much of the initial work on each of the graph coloring was done as a consequence of investigations related to coloring maps, such as those found in geographical references. So kind of just like if you're looking at a map, like in elementary school, middle school, or you just pull up a map of the, any country with their different provinces inside or states, you would see the different colors. And coloring countries in a map, it is customary to use different colors for countries that share a common boundary. This convention makes maps much easier to read. The question arises, what is the smallest number of colors needed to color a map? So in figure 4a, we see a map that can be colored with 3 colors. So let's take a look at that. So we have red, green, and then red and blue. Well, if we draw what's called a dual graph of this to kind of see why we can do this with 3 colors. So I'm kind of introducing this idea of a dual graph real quick, and then we'll talk about it. So in this case right here, we would have vertex 1. That would be our red. And then we would have vertex 2. And that would be our green. And then at that point, we could go off and go like this, call this vertex 3, call this vertex 4. Vertex 3 could now be red again, and vertex 4 would have to be blue. Now, the reason that we would need that blue is because of the connection. So because of the adjacency. And so let me hit pause. I feel like I just said something incorrectly. Sorry, I just I practiced this and I was like, okay, I'm good to go. So I can go red to green and then back to red. But because of the fact that red and blue are adjacent to each other, I can't have this blue location down here, vertex 4, be red also, even though it's not adjacent. So even though vertex 4 is not adjacent to vertex 1, because we use red for vertex 3, and vertex 3 and vertex 4 are adjacent to each other, I need a different color to be able to meet those requirements. And so in this case right here, we would have we have 3 colors, 1, 2, 3, 4. Excuse me, I can't count. Red's used twice, so we have 3 colors there. All right, going on to the next graph. So in figure 4b, we see that we need 4 colors for that and not 3. Now the reason is if we make the dual graph of this, it kind of points it out nice and neat for us. So let's call this vertex 1, that will be red. Then let's go off of this, and at this point, red can either go to vertex 2 or vertex 3. Vertex 2 is blue, and vertex 3 is green. And then these guys both go off, or these vertices both go off to vertex 4, which is yellow. Now, why couldn't we use red for vertex 4? Well, it's because what's happened here is that we have some adjacency. Red is also adjacent to yellow because it's inside of this graph here. And so we see that since red also is adjacent to the yellow, we would need a separate color for vertex 4, and that's why we got yellow. That's why we need 4 colors for this graph. So the statement of the map coloring problem sounds suspiciously like the statement of graph coloring problems. Indeed, by regarding each country as a vertex and connecting two vertices in their countries share a common boundary, we can produce a graph called a dual graph of the map. If we're able to find a coloring of the dual map, it will provide a coloring of the map. So note that 2 countries that touch only at a single point are not regarded as sharing a common boundary, and so that wouldn't apply. So that's just kind of a side note. If you're kind of looking at maps, you're like, oh, why are these 2 countries the same color? It's because it's such a small area. We're looking at a larger amount of surface area that's contacted here in these graphs to be able to think about these dual graphs. All right, so here we go, wrapping up. We got a couple examples to take a look at. So let's see. So actually, this is one example that we're going to work through. So example 3, find the dual graph of the map from 5a. Color the dual graph with the minimum number of colors, then display the coloring of the map that corresponds to the coloring of the map, or the graph, excuse me. So in figure 5b, we have a dual graph. Notice that the vertex has replaced each country. So we have, I'm going to label these with like vertice labels. So let's call this vertex 1. So vertex 1, and then vertex 2, and then vertex 2. And then we'll call this vertex 3, and vertex 4, and vertex 5, and vertex 6. All right, so now let me pull this up out of the way. So notice that a vertex has replaced each country. In figure 5b, we also find a coloring graph using 3 colors. So why just 3 colors? Well, because of the fact that we have vertex 1 and 2 are adjacent, so they're different colors. But then we go to vertex 5 or vertex 3. Those vertices 5 and 3 are not adjacent to each other. So we can go back to red. We can go back and use that same color again. However, we need a new color in the middle because that vertex 4 is adjacent to these reds. And then last but not least, we can go back to blue because that way we're trying to minimize our colors and we don't have any adjacency. So in this case here, we come out with our coloring of our map and associated that in 5C and kind of get the idea. So our minimal number of colors would be 1, 2, 3. So 3 colors that we could do this in. All right, so that would be our and so our chromatic color for this particular mapping would be, or for graph would be 3, because we have 1, 2, 3 colors to be able to do the dual graph. All right, hopefully this helps you get through the homework. Pretty straightforward, still no proving anything, just applying these concepts and kind of maybe just building some background knowledge for future math courses.